Hey folks, we're almost done. We've only got about 7 more problems to go, 5 of them on this worksheet. So, let's get started. Here we have 4.3 grams, 4.35 grams of C5H12. Alright, so C5H12. And what are we doing? We're reacting with oxygen. So obviously this is a combustion reaction, so we produce CO2 and we produce H2O. Alright, so we have to have 6 of these, we have to have 5 of these, we have to have, let's see, 3 plus 5 is a total of 8 of those. So we now have a balanced chemical reaction. Okay, so now what do we have to do? We have 4.35 grams of this stuff. 4.35 grams, and we have 4.00 liters. Be very careful when you do this. Here we've got 1 in grams, here we've got 1 in liters. So when you do the math, you just have to remember to do your conversion factors right. And this is why we always write down all of our units. Right? Now, which of these two products do we go to? Well, in all honesty, it doesn't matter. Right? We could go to liters of something. Oh, that's really easy. Then I don't have to figure out masses. Now, in my case, I do know how many, what masses are, but let's go with liters. Let's go with liters of carbon dioxide. Okay, that's my choice. You can go to grams of carbon dioxide. You can go to grams of water. You can just stop at moles for that matter. That would work as well. Okay, so I'm just going to start with my pentane and say I have 4.35 grams of C5H12 and I'm going to go from grams of C5H12 to moles of C5H12 and from moles of C5H12 I have to go to moles of my target, which in my case is going to be carbon dioxide. And as I said, you could have stopped right there if you wanted to. I'm just going to go to liters of carbon dioxide because it gives me more, moles to liters, because it gives me a better visual of what's going on. And I tend to like visuals. Okay, now I'm going to have to do exactly the same thing for oxygen. But let me finish this one first. C5H12 I have to figure out weighs 72.150 grams in 1 mole. And I look at my molar ratios here, and I have 1 mole to 5 moles. And I know that 1 mole of CO2 is 22.4 liters of carbon dioxide. That gives me 6.75 liters of carbon dioxide. Alright, let's do it again, but this time we're going to do it for our oxygens. We have 4.00 liters of oxygen. And I have to convert from liters of oxygen to moles of oxygen, and then from moles of oxygen to moles of, again, carbon dioxide. We have to go to the same thing. We have to be consistent. And moles of carbon dioxide to liters of carbon dioxide. We know that they're 22.4 liters in a mole. We can do that twice. So they're going to cancel each other out. And moles of O2, we've got 8 moles of O2 going to 5 moles of CO2. So when I actually do this math, I come out with 2.50 liters of CO2, which tells me that I can only produce 2.50 liters of CO2, which means I have excess of my C5H12. So how do I figure out how much excess reactant remains? Well, what I can produce is 2.5 liters, so I have to subtract that from 6.75, so minus 2.50, right, and that gives me 0.25, that gives me 4.25 liters of CO2 gas. So now what do? Well, I work backwards. I start with my 4.25 liters of CO2 gas, and I want to figure out how much of my excess reactant do I have left over. Well, clearly I used all of my oxygen, so I have to work my way back here to the C5H12. So I have to go from liters of CO2 to moles of CO2, and from moles of CO2 to moles of, in our case, C5H12, because that's what I had excess of, and I go from moles of C5H12 back to grams of C5H12. And this will tell me how many grams I had left over. Well, there are always 22.4 liters in 1 mole at standard temperature and pressure. I had a 5 in front of my carbon dioxide and a 1 in front of my C5H12. And 1 mole of C5H12, we already figured out earlier, was 72.150 grams. So I do the math there, and that gives me 2.74 grams of C5H12 was not used, and the remainder was. Okay? That's it for number 16. Number 17. Right. Zinc reacts with excess silver nitrate. Zinc reacts with excess silver nitrate, AgNO3, to form how many grams of zinc nitrate? Zinc nitrate, NO3, plus the thing I have to have left over is silver. That's a single replacement reaction. Let's make sure our charge is balanced. We have a +1, -1. That's cool. We have a +1. Oops. We have a +2, -1. So we have to have that, which means we have to go and balance our equation by putting 2's there. All right. So now we're ready to do some math. We have 3.0 grams of zinc, and we have to convert from grams of zinc to moles of zinc, and then we have to convert from moles of zinc to something. So what do we choose to go to? Well, it's asking us how many grams of zinc nitrate we're going to have. All right, so we have to go to grams of zinc nitrate. So we're going to go to moles of zinc nitrate. And from moles of zinc nitrate, we have to go to grams of zinc nitrate. Grams of zinc nitrate. All right, so 1 mole of zinc, I have to look that up on my periodic table. That's an easy one. That's 65.39 grams. And 1 mole of zinc gives me 1 mole of zinc nitrate. And I got that from my coefficients up here. And 1 mole of zinc nitrate, I had to figure that out. That's a rather complicated one, but that's 189.398 grams of zinc nitrate. So I do the math, and that gives me 8.7 grams. Notice I only have 2 sig figs, 8.7 grams of zinc nitrate. And that's it. Okay, that's number 17. How about number 18? We are starting with barium carbonate. That's BaCO3, barium carbonate, decomposes into how many moles of barium oxide? Well, that's BaO, and the other product is carbon dioxide. All right, well, let's see how this works. We've got 1 barium. We've got, well, barium's +1, +2, carbonate's -2, so that's balanced. +2, -2, and carbon dioxide's obvious. We have 3 oxygens, 1 carbon, 1 barium. We are balanced, which makes that really easy. All right, so we start with 8.2 moles. 8.2 moles. Ooh, moles. I don't even have to do grams. 8.2 moles of barium carbonate. Okay. And what am I going to? Well, I'm going from moles of barium carbonate to, I want moles of barium oxide. That's what it's asking. Moles of barium oxide. Well, look at that. We're done. Okay. So, we have our target units at the end, so we're done, and we have coefficients of 1 in both cases. So our answer is simply 8.2 moles of BaO. Now that was the easiest problem you had to do all day. So why did I put it here? Well, the reason that we put this one in is to make sure that you didn't go through this huge stoichiometry problem, realizing that you're balancing your units. You started with moles, you ended with moles. Much easier problem than you first might have thought. Okay. Number 19. We have 4.5 grams of sodium hydroxide, NaOH, 4.5 grams of sodium hydroxide, and it's reacting with 2 grams of sulfuric acid. Sulfuric acid is H2SO4, and that's 2 grams, 2.0 grams. How many grams of water are formed? Well, this is a double replacement reaction, and it produces H2O, and it produces sodium sulfate. And sodium has a +1, sulfate has a -2, so that's Na2SO4. Everything else is already balanced. The sodium has +1, -1. Right? To make this thing balanced, we have to put a 2 in front of here. That's going to give us 2 waters. So we are now balanced. And it's asking us for grams of water. And this was 2 grams of sulfuric acid. Okay, so let's see how much stuff we come up with. We're trying to figure out how many grams of water are formed. This is a limiting reactant problem. So 4.5 grams of sodium hydroxide. I have to convert from grams of sodium hydroxide, moles of sodium hydroxide, and from moles of sodium hydroxide, we have to go to moles of water because that's what it's asking us. That's our target. We go from moles of water to grams of water. Okay, so clearly what we have to do is look up sodium hydroxide on our periodic table, calculate how much that weighs. Right, I have lost my pointer. There we go. Thank you. That's 39.997 grams of sodium hydroxide in 1 mole. And I notice I have 2 moles of sodium hydroxide giving me 2 moles of water. I have to use my coefficients up there. And then 1 mole of water gives me 18.015 grams of water, which, when I do the math, gives me 2.0 grams of water. Again, notice 2 sig figs in my problem, 2 in my answer. Now I start out with 2.0 grams of sulfuric acid, which is H2SO4. Think of it like hydrogen with sulfate, because it's sulfuric acid. And sulfate has a 2- charge, that's why there are 2 hydrogens there. You have to get rid of grams of H2SO4. Go to moles of H2SO4. And from moles of sulfuric acid, H2SO4, we go to moles of water, because that's again our target. Now it's going to look exactly like what we have above us here, because we're still going to grams of water. We have to be consistent. So that's 18.015 grams of water in 1 mole, and water has a 2 in front of it, and sulfuric acid only has a 1 in front of it. It's an implied 1, and 1 mole of sulfuric acid is 98.078 grams. 8.078 grams, and we do the math here, and we come up with 0.73 grams of water. So clearly, this is the maximum we can make. We ran out of H2SO4 first, so that's our limiting reactant is H2SO4. The answer that we're looking for is over here. 0.73 grams of water is the maximum that we can produce. That's our expected or theoretical yield from this equation. All right, last one for this podcast. We start with 8.0 liters of butane. Butane is C4H10, and it reacts with oxygen. This clearly is a combustion reaction, giving us carbon dioxide and water. Right, now you notice we didn't even mention the water in the problem. Well, that's okay because you know that it's a combustion reaction, so you should be able to figure out exactly how that works. All right. It looks like we have to have 5 waters, but then we're going to have an odd number of oxygens. So I'm going to double this, and that's going to give me 8 of those. It's going to give me 20 hydrogens, so that's 10 over here. That gives me 5 O2s plus 8 O2s is 13 O2s. So there is my balanced chemical reaction. Right. I start out with 8.0 liters, and I'm trying to figure out 50 grams. Oh, 50 grams of carbon dioxide. Interesting. That tells me what I'm looking for is my percent yield. So I start with 8.0 liters of butane, C4H10, and I'm going to have to go from liters of butane to grams of carbon dioxide. So liters of C4H10, H10 to moles of C4H10, and then from moles of C4H10, I go to moles of CO2. And from moles of CO2, I have to go to grams of CO2 because I have to compare it to my 50 grams over here. Well, I know that there are 22.4 liters in 1 mole, and I've got a ratio of 2 to 8 in my moles of C4H10 to moles of CO2. 1 mole of CO2 weighs 44.009 grams, and when I do the math here, I come up with 63 grams of CO2. So this is my theoretical or my expected yield, and what the problem tells me is that I got 50 grams, and I was expecting 63 grams. I multiply by 100%, and that's going to give me my percent yield, which is 79%. So that's my answer. Right? That's it for this podcast. We have 2 more problems to go. That's in the next one. I'll see you in class. If you have questions, let me know. Bye.